So welcome to the session transitioning from the built-in render pipeline to URP and HDRP. My name is Mathieu Muller. I'm the lead product manager for graphics. With me, my awesome colleague, graphics product manager Oliver, in charge of the rendering foundations. And we have a big honor to have Onat, the co-founder of Slowbros and creator-director of the fantastic game that I don't know if you've played it, Halibut. So we will, like Oliver and I, will be converting a built-in project to URP and HDRP so that you can see the steps, the difference, the benefits. And Onat will tell how, like starting 10 years ago on the built-in render pipeline, he leveraged HDRP to probably, honestly, like it's probably one of the most visual stunning game of the year. Yeah. And it's not just me saying this, but the articles as well. And he will show this opening the actual Halibut project on his computer. So first, like if you are on built-in render pipeline and you're afraid that SRPs are not production ready, in fact, in 2023, already 90% of the Unity games released on Steam were using SRPs, and more than 50% again were using it on mobile and XR. On the asset store, we did a selection of like top 100 plugins and assets, and actually the URP is the most compatible asset on the store. And if you have a project on built-in, like don't worry, our goal is not to force you to move. Our goal today is to just show you the benefits and the steps to get there. Don't worry, it will be maintained on the 6th generation. It's going to be a longer generation than usual, so you will have like plenty of years to transition. But just know that after that, we will remove it, but we will unify the pipelines, which will be amazing. I'm super excited about this. So what are the differences between the pipelines? If you want to know more, like it's extracted from the doc, so you can find the same information and actually like a very extensive list of every single features. I've done it and spent evenings doing this. So check it out. And just very quickly to have a summary of the differences. So in terms of extensibility, really like you can leverage like the custom passes, custom render features, custom post-process to be able to cleanly create your own features into the pipelines. You have access to the C# source code if you want to fine-tune some performance, if you want to change something core in the engine like shadows. You can do it. You have access to VFX graph. For shaders, we don't have surface shaders, but almost everyone we talk to, especially on mobile, and they want to write shaders, they take Shader Lab, copy the URP lit or URP simple lit, and from there are reusing the core functions and just tweak the things that they need. But a lot of people are using shader graph, which is a bit more advanced in SRPs, allowing to do custom passes and custom post-process. For lighting, we have adaptive pro volumes. I hope you maybe watched the lighting talk this morning. And for lights, we have also a lot more things. In URP, we have the rendering layers, we have decals, we have like code shader, like for the surface as well. And tons of advanced things on HDRP off the shelf, like advanced materials, advanced reflection probes, screen space effects, and so on, sky, water, volumetrics. And finally, for performance, that's really where it's days and nights. We've made tons of efforts in the past years to improve performance so that you can leverage like the low-level hardware. And also, I recommend watching the talk from Oliver and Damien from yesterday, if you have not watched it, or you can watch it online. And finally, the compatibility with dots and entities. So we looked at a lot of project reviews, interviewed a lot of people to know exactly why they moved to SRPs, what were the benefits. So first, like just at the top, people said long-term maintainability, like you get the latest fixes, you get probably the most numbers of running devices on the world with SRPs now, to be able to target new platforms. And otherwise, it's in 3 buckets, better visual fidelity. So people tend to move to URP to get like a visual boost, having better lighting, better shading, better global illumination and effects. Being able to scale content, Oliver will show this as well, that even like if you have a simple scene, the two can be similar, but when you start scaling, it's like the difference really shows. So if you want to put more things, and then like the other one is to remaster an old game or to make a PC console version of a game. Then better workflows with built-in, since like it was extensible, but you could not really cleanly add things deeply or extend it more cleanly with custom passes. You had to do a lot of workarounds, or you had to do like more batching and more tricks. Now you have the SRP batcher to help you do this. Improving productivity and recruitment. You have still a lot of tech artists who prefer using node-based shaders. Improving debugging and optimizations. So we have tons of tools for this in the render pipelines, specifically the rendering debugger. I go fast because we will see them in the demos after. And also simplify the quality settings. With the SRP assets, you can really simplify your management of quality levels. And finally, being able to optimize. It's the longest slide of the presentation. So being able to reduce the build size, because you have more control everywhere with the SRP batcher, with lesser need to batching or to atlasing, you can really optimize this part. Being able also to reduce memory usage, improve CPU and GPU performance, either leveraging better like the modern graphics APIs like Vulkan or using compute, but also like using upscalers and dots and so on. And then replace also suboptimal systems. That's a big one. We see a lot of people who are using a lot of cameras in built-in render pipeline. And like with custom render features, you can replace it with something much cleaner and much more performant. In some like very big games who upgraded, like they could see like 40% performance improvement just by like better managing the cameras. And then you can optimize deeper again with SRP C# source code, remove what you don't need. I don't know if you've seen the Ubisoft presentation yesterday. Like it was really a lot about this, how they could tweak the pipeline. So how to upgrade? First, like don't just upgrade and jump on it. Like you have tons of resources to help you accelerate. So the URP 3D samples, like just explore them before going there. There are tons of things that you can reuse. Like check how it's set up. The 2D sample projects to see how the URP 2D lighting features work and can be beneficial. And then especially these ones that some people don't know. If you go on Package Manager, if you click on multiple packages, you have samples. And for example, a big step is to convert your shaders to often shader graph. There are tons of resources where you will be able to have almost like your shader that you wrote yourself, like almost ready with shader graph samples that you can reassemble. We have tons of ebooks as well. So if you want to learn about these new systems that you don't know, we have tons of them on unity.com how to. And we also updating these ebooks so that they are up to date with the versions that you're using. So for example, the Unity 6 URP ebook, like I think the third generation of the ebook, the third version, is coming soon. And we will be upgrading like the ebooks to Unity 6. So then you just need to choose your render pipeline. So very simple. If you're doing 2D, if you're doing 3D mobile, if you're doing 3D targeting a wide range of platforms and you don't want to change the content, and if you're doing non-physically based rendering, URP. If you're doing 3D, high fidelity, physically based rendering on PC and consoles, just use HDRP. Never do custom SRPs, no, I'm joking. It's just very hard to do, but some people like doing it. To be honest, like most people don't do custom SRPs now. They usually branch off one of the SRP and kind of create a custom version of it because you have integrations of shader graph and VFX graph. So it's mostly recommended, and it requires more advanced teams. And then finally, you can port. So what's the steps to port? A lot of steps, right? But you will see that Oliver and I, we do this in 10 minutes. Probably not in your game, right? So what we recommend is actually upgrading a level or two just to see how it goes. Like Bleaksword, DX, they tried one weekend and then the end of the next week it was done. It's not typical. Like on a big mobile game used with 40 million users, usually, like a lot of studios have done this, but it takes usually a year, not a year of full-time everybody working on this, just like 1 or 2 person part-time doing the move together with like a new version of the engine. So incorporate it together. So let's jump into it and having Oliver taking a project, and the goal is just to say built-in URP and then see the differences and what are the steps.
Perfect. Thanks, Mathieu. So let's have a look at a concrete example of upgrading a built-in project to URP. We have picked this classic example from the asset store. So it's quite old, and it's available for you to download now. It's a built-in project. There's also a version of it of URP, but just the assets, so like just some parts of it. So we thought it's a good idea to just bring it over fully to URP now. And our first goal is to convert it to URP, but without any content changes. We want to not modify any lights or materials, and we still want to reach a nearly identical look. And this could be quite important for you if you want to upgrade an existing game that has a lot of levels and many materials and lights. If your game is simpler, it might also be worth to remaster the content with the new features. And Mathieu will later present some ideas about that. And after we have converted the project and are happy with the results, we also want to compare some metrics between built-in and URP and see how both pipelines scale with more content added. The project opens smoothly in Unity 6 editor without any issues. And now let's set up URP to begin the upgrade. First, we are installing the universal render pipeline from the package manager and create a default RP asset. And this is also created then a URP renderer for you. URP has a couple of points of configuration. This helps you control the scalability, which is very important to reach all platforms with the vastly different hardware characteristics they come with. Quality settings, which is where the bulk of the options for the built-in renderer pipeline were put, is still used. And these settings influence any pipeline and are the same between the SRPs. The quality settings have levels, and each level is assigned a pipeline asset. And the pipeline asset is where most of the URP settings are configured. A pipeline asset is in turn references a list of renderers, and a renderer has a list of renderer features. So this is quite a lot to keep track of, but the system is very flexible and in terms of scalability and customizable, like unbeaten. In addition, you have a very powerful volume framework, and that is also optimized for low-level hardware now in Unity 6. This allows you to adjust the effects and the look and the feel of the game either globally, per quality level, and also dynamically depending on the position in the scene. Similar to what you might know from the post-processing stack v2 and the volumes there. After we have set our render pipeline either globally or in the graphic settings or in the current quality level, URP is then activated in the project. And don't be afraid of the famous pink materials. Let's just upgrade the content. Our starting point, and really highly recommend to start converting, is the render pipeline converter. You find it under Window, Rendering, Render Pipeline Converter. And this is really like a great tool to convert our existing rendering settings, standard materials, animation clips, and post-processing effects. And it also converts all the different quality levels. After automatic conversion, you might have some custom shaders that we need to convert. And you have multiple solutions to port them. You can fully re-implement them in shader graph, or you can also extend the shader graph capabilities with code blocks in HLSL shader language, or you can choose one of multiple URP shaders that come out of the box. You can also adapt these or implement your own version of these via modifying the source code. Using shader graph is normally the quickest way to update a custom shader to URP, especially since you don't need to start from scratch. We have a vast library of shaders and shader feature samples available to you directly in the package manager. For example, the node reference samples are a collection of over 140 shader graph files, each one representing a shader graph node. You can use these as reference to learn how shader graph nodes work and what they do. And each file contains a description of the node, explains its functionality, and breaks down the math under the hood. We've also created the feature examples for shader graph, and this set provides examples of popular shading techniques such as interior cube mapping, parallax occlusion, or vertex animation. And another sample we just released, we saw it on the right, is the production-ready shaders. It's a collection of over 25 pre-built shader graph shaders that are ready to be dropped directly into your project and can be used to create realistic-looking environments. For this project, we have decided to recreate the toon shader with shader graph and extend it with custom HLSL nodes for the toon lighting. It is important that you give your new shader graph the same names as your build, like you see on the top left. Like the variable names should match the built-in custom shader ones so that they directly convert when we assign the new shader. And there's also the subgraph, and that's where we then implement the custom HLSL. And this subgraph contains the HLSL block, so we see how the function name and the properties are then exposed into shader graph. And this is a great way to reuse or adapt your existing shader code. URP comes with standard shaders out of the box. The main one is lit, a PBR shader similar to the standard shader. But a little more complex. For more performance, we have a simple lit and a baked lit, which can be important for stylized games. And as I said, you can also copy any of these and adjust it to your own needs. This has several advantages since you have full control over what and how it is rendering. But you also need to be sure about the complexity of it. So many studios we talked to managed to keep track of some of the tweaks in the shader and were very happy with the process. After we have picked our solution and recreated the shader, we can find all references that the custom shader from built-in uses in the whole project. Just right-click on the shader and pick Find Reference in Project. And then in the search window, you can just select all the materials. And in this inspector, just choose the new toon shader graph. And all materials are then from pink converted correctly here in this example. And now that the settings and materials are converted, let's match the lighting. In the first place, it looked like the one on the top. So this is like URP standard lighting. And one important difference between built-in and URP is the lighting fall-off. So URP implements the inverse square to mimic real-world lighting. This is more realistic, but we would need to change the lighting intensities if we want to get the same look as our initial sample. On the bottom, you see how we changed the lighting in URP to match the built-in look. Maybe you notice the difference, for example, like at the fish or at the character light. This change is achieved by modifying the URP functions that implement the lighting fall-off. The two functions in real-time light HLSL need to be modified to get closer to the built-in look. On the right, you can see how our changes compare. And this is just one proposal we have picked here to get closer to built-in. So the functions you see here can be directly used for this. SRP comes fully equipped with the source code, which is different to what you know from built-in, where a lot of the calculation is happening under the hood, deep inside the engine. This is great to understand how the render is implemented. And for modifying the source code, you can just move the URP folders from the package cache to the packages folder. So just drag and drop them. But remember, with great power comes great responsibility. Be sure what you are doing, and it needs to be redone with every editor upgrade. But if you just have some tweaks, it should be fairly simple. If you have graphics experts on your teams, you can create truly unique rendering styles with it. Since the sample game uses a lot of baked light, which might also are very common for your projects, we also need to change how the light mapper calculates the light fall-off. And this is as simple as changing this fall-off type to legacy. And after rebaking, you will see how the baked lights are then identical to built-in, since it uses the same light baker under the hood. The original project uses gamma lighting. So we also stick to this here to not need to adjust our lights. But it is absolutely recommended to leverage linear lighting to achieve a more modern look in your game. If we look at the results, with very simple steps, we ported this project like the simple sample game with a nearly identical look. After installing and activating URP, we replaced the surface shaders with a shader graph using custom HLSL nodes and assigned this project white. We then modified how URP calculated the light fall-off, thanks to the open source nature of SRPs. And then we still used gamma lighting similar to the original project. Yeah, he's buying now or she or he is buying a coffee now. So. So now let's look how the two pipelines compare on scalability. If we look at the frame debugger, we can already see that SRP has less draw calls and set pass calls accordingly. This is thanks to the SRP batcher that can not only batch the same materials, but the same shaders. Now let's stress test this. So they start very similarly at the similar CPU time, or this frame time. And then we spawn up to 3,000 random models from the project with random materials from the project. And you see how URP scales better. And then if we add up to 8 real-time lights on the right, so there this chart continues basically, we can see that this also scales better with URP. And in URP, we also have forward plus to remove the limitation of 8 real-time lights, similar to what you might know from deferred rendering. And speaking of deferred, in Unity 6 with render graph, we have a very optimized deferred renderer, and that is especially beneficial on mobile. Because render graph merges the passes on the mobile processor and only uses the G-buffer textures on tile without reading and writing from memory. And this is an important improvement on mobile devices and can reduce the heat significantly. This leads to longer battery life and also better performance, since the device might not start throttling when it's getting too hot. In this example, we measured on an iPhone 14 Pro and we saved 60% bandwidth usage by using URP deferred instead of built-in deferred. And this is a huge difference. And this is achieved with render graph, which is new in Unity 6 in URP and can merge the passes on tile, as I said. As you see, all the 3 main passes are merged together with the deferred lighting, and as we can see in the render graph viewer, all G-buffer textures stay on tile, which leads to the reduced memory bandwidth we have seen. And that's also, by the way, here in the chart, you see that it's in Xcode, you can see that there's no activity on the memory, while on built-in, it's like a highly read and write operation. And SRPs are meant to be scalable. URP can be a very minimal pipeline and in its leanest configuration. And then it scales with more effects you are adding to get most out of the target platform. Here are some examples of different complexities presented through the render graph viewer, also in Unity 6, from a very simple forward pipeline directly, so that's directly rendering to the back buffer, to a more rich deferred pipeline with effects like SSAO or bloom. And now that we have seen how we can migrate a project to URP, and you understand how scalability is directly built into the system to get the best out of every hardware, I will hand it back to Mathieu with some ideas how you could leverage the higher end of our SRP spectrum to remaster content like this.
Okay, so good. Okay, so I will start from where Oliver started. I just set the global HD render pipeline asset and HDRP asset just for the saving some loading bars. And I also used the HDRP wizard here, which allows to automatically convert to color space to linear color space, convert the light map encoding. And from here as well, I can convert all the built-in materials to HDRP. So we see that a lot of the materials are still using the toon shader. Okay, here. Come on. Okay, here. So for this, my solution was just to ask AI to write me a small tool to convert all the materials which have a surface shader, toon shader, and are reused with a shader graph shader that Oliver made. So just to take like Oliver's shader made with shader graph with URP, I just add an active target HDRP, and then it can work across the board. So now I can let this tool do the work. As you can see, it's still very dark because HDRP is using physical light units. So you need to have exposure. So I will create a camera volume and with a new component and just add exposure, set to automatic histogram, and then put the limit, min, and max. So you see that it was pretty fast to get there as well. I will, like to be able to push the visual fidelity, I want to have fully real-time lights. So I clear the bake lighting. I don't know if you're using this. The Light Explorer is super useful, where you can see all the lights, reflection probes, and so on. So I would just select all the lights and make them mixed for now. So now I'm ready to go, and I can start pimping the project a bit. So, of course, like what could make things look better is to have a bit of fog. So I will add the sky and fog volume. We can see that the sky is dark because there is no directional light. And I will put the volumetric fog distance, attenuation distance a bit closer. Now what I want to do is to have like this nice light coming from outside. So I will take this spotlight here and push a bit the intensity until I get these nice shadows in the volumetrics. We can see, as Oliver mentioned, that the range and attenuation are not exactly the same. So here, I will push the range a bit further so that we can light even the character here. Then we go closer, and we see that the resolution of the shadow is not great. So we can see how the scalability settings of the render pipeline helps managing your quality settings. So here I just say that this light has to be a medium quality setting. And because we're using HDRP, which has PCSS shadows, I can push a bit the radius of the light. So like we can have like blurry shadows at the top and sharp shadows at the bottom to have nice lights. And then finally, to push a bit I will want to also have a more natural light here so that it doesn't feel as much, yeah. Okay. And then I will want to tint the shadow. So we can tint the shadow. So yeah, it makes no sense to tint it red, right? But we can tint the penumbra, and it gives this kind of chromatic aberration, which is nice to have on the shadows. Okay, so it's pretty nice. Again, like if you want to pimp your asset, like Package Manager and the samples are pretty nice. We have some people here who made a lot of content here. So if you go on Package Manager, high definition pipeline, you have, for example, volumetric samples here that are imported in the project. And here I can directly go into the prefabs of these samples, which are pre-made for me. It's using shader graph, so you could customize it. And we will add a ground smoke here. And there is like this fumes one that I really love, which will kind of simulate the projectors there, going like doing some interesting lighting stuff in the fog. Okay, it's pretty pimped. Let's move to reflections. So for this, we always start with putting a reflection probes, which will be the fallback for everything. So I add a reflection probe. And I will set this to real time for now, every frame, and we can have time slicing so that it costs not so much, even if it costs a lot usually. And then I will go into ISO top-down view to kind of adjust the light probe. Okay, good enough. So yeah, we are 3 minutes in, 4 minutes in, and we have already like something quite interesting. We can see that it's not so interesting here, the reflection probe. So because I would like to really have like this reflection of the desk. So for this, I will add screen space reflections. So here it's something super useful. You know, it's not active in the pipeline, and usually you were searching for half an hour where is this setting. Now you can just click that, and it just takes you to the place that I have to click. But here I have a problem, right? It's enabled, but I don't see anything. And that's where the rendering debugger is very interesting as well. You have a lot of modes to debug And for example, we have a full screen debug mode for screen space reflections. So we can see here that, if you're doing screen space reflections, you don't want to rematch the entire screen. You want this where it makes sense. And if we go back to the screen space reflections, we can see there is a minimum smoothness to do this. And if we put it down, we can see that we could do this only on the ground or maybe on more shiny materials. But this would make no sense to spend your time on this. So I just want to place it on the ground. In my case here, I will put this back up. And instead, I prefer, let's reset I prefer to push the smoothness of the floor. So, OK, now it's there. So nice reflections. Let's move to global illumination. So I will, one thing which is not great here is this desk doesn't really feel attached to the ground. So I will add some ambient occlusion. And we can see that the actual ambient light doesn't affect much things. You need actually to push the direct lighting so that it's kind of better attached to the ground. OK, now it's much better. And then we can check that it's not done full resolution, so it's not too expensive. I will add a screen space global illumination, which as well is not active in the project, but again, it takes me a second to get there. And here, sometimes you will see this message about the rendering debugger. It's because the rendering debugger overrides the settings. So you can just reset your rendering debugger, and it's good to go. Then I can enable it. And you can, if you look there, you will see that it's very slight, because there are not so many bounces of lights. What we can do, which would be interesting, is we have these lights here, which are just emissive surface, so not really real lights. And with SSGI, it will be able to actually light the environment here. So if I push the emission intensity, you look at the seat, you should see that it really behaves like a light because we have screen space GI. OK, so we are pretty good. Let's just finish something. There were some lasers there, so I will just add the lasers. For that, I already prepared just a normal lit material with some emission setup for me. And I would like this to be very glowing a lot so that it really feels warm. So I will add some bloom. And I will push the intensity. But you see that the problem with bloom, it's kind of blurring everything. So be careful with bloom. It can remove the sharpness. So I'll put it quite high. But fortunately, we have this threshold that will allow to get back the sharpness of the less bloomy characters. Yeah, I know that lighters hate me doing this, but I think it's still my choice. And finally, maybe one last thing we can do is there is a small light here that I really liked, and it's animated. So this one, same thing. I already created a version with shadow graph so that I can have exactly the same name of the property, so that the animation still works. Here, what I would love to have is screen space reflections. Screen space lens flares, which are also available in URP, by the way, same as rendering debugger and many things that we've seen. So screen space lens flares, and they're pretty nice because they work automatically, right? Like I put them here, they work on the highlights. Because we are a sci-fi game, we can put some light streaks, and about lens flare, it's all about not having too many of them, and that's here. It's pretty good, right? How long did it take? 10 minutes about to pimp up your level. So pretty good, no? I didn't change any content.
Yeah, and by the way, the pixelated here, it's not on Mathieu's screen, so it's the wall probably. So it's super sharp on the display.
So now let's look at the performance, right? So we look at the display stats. It's pretty miserable, right? I had too much fun with my frame rate, and we can see that we are uggily GPU bound. I would just check the profiler and run it just to check, how things are going. And I can see, this is waiting for the GPU to have finished. And this is the actual render loop, which corresponds basically to the gameplay. And I can just check, like 3 milliseconds is even too much, I think, for that. And we can see that there is a lot of log string to consoles. So if we look here, there is no audio listener, stupid me. So I just add this quickly. Okay, so now it should be better. And okay, so let's look at this. It's slightly better now, and still like we gain some time on the CPU, even if it was waiting for the GPU. But let's look at the detail stat on the rendering debugger. So I will just update this. And we can see that actually not so much is happening. Like many of the things are less than like 0.01 milliseconds. But this one, like 1.2 milliseconds of rendering shadow maps is a bit too much. So what I do is using shadow caching, which is in HDRP at the moment. So again, using the Light Explorer, I can take like all these lights, and you see that like a lot of them are casting shadows, which I don't need to. So instead of casting shadows every frame, like I could just like have the shadows being done once and then just reuse that shadow map. So now it's really good, except that, yeah, if I move this character, then its shadow is cached. So that's not great. But that's really the main shadow I would like to have. So ideally, I want just to draw the shadow of these dynamic objects. And if I select this object here, if I move it around, you can see that the shadow is updated. But if I put it as static shadow caster, it means that it will be part of the cached shadows. So now if I like relaunch the caching, so if I cache it now, and I move this wall, you see that the shadow is cached here on this light, but the character is only drawn, which is pretty nice. So now what it gives is that I just have to render the shadow for basically one geometry, and that's all. So let's look at the rendering debugger again. And it's pretty nice. We gain a few performance again, like probably there are some other things happening, but we see that the rendering shadow maps is down to 0.1 milliseconds. So like one thing I know that I was too crazy about was SSGI and SSR and ambient occlusion, all this stuff, which like at QHD on my little laptop is a bit violent. So the rescue for that is, of course, dynamic resolution. So let's enable this. And we will force the screen percentage to 10%, and it's not working. You might say that to yourself. It's because you need to enable this on the camera. Actually, I didn't have anti-aliasing before, so maybe that didn't anti-alias the pixel of the screen. And we can enable dynamic resolution. Oh, no, look how beautiful it is, right? No, look at this. 5 milliseconds on the GPU. So it's perfect, ship it. No, of course, like 10% is crazy. It's 200 by 100 pixels, something at this scale. But we have this magic upscaler called STP, which already, like at 10%, you see like the quality getting up. And then if we put something to more reasonable, like 50% of the screen, we almost get back like the full fidelity. And now we are like at 40 frames per second. So it's pretty nice. I could even push it down really for like lower end platforms. Let's continue a bit. Like I've seen something here. Like I have the volumetric clouds. Like why do I need volumetric clouds here? It's indoor. So I will just clean up a bit the things. Because what you have to know, Oliver showed that, is in analysis, we can also look at the render graph viewer for HDRP. And we see why HDRP is so powerful. It's because there are so many passes and so many resources being used. Don't worry, it's like the memory is reused, but probably you don't need that all the time, right? Like of course, I had fun, so I use a lot of them. But we can have like, there are many things that I see, for example, the debuffer here that I don't need because there are no decals and so on. So let's clean up a bit the settings. So first I will remove some passes that I don't need, like I don't have much transparency here, so I don't need the depth pre-pass, post-pass. We were saying that I don't need volumetric clouds. I don't need, I think I don't need decals here. Like we can see here that it's gone from the rendering, from the render graph viewer. And we don't need, like I do this very quickly. Probably I could remove more. We don't need distortion, subsurface scattering, right? So now it should be a bit, it's still heavy, but it's still, it's better. We had almost 50 frames per second. And so it's getting there. Like if we check, we don't have these volumetric clouds here. So what else should we do? Sorry, I forgot. Oh yeah, one thing which was really not good that I totally forgot is this real-time reflection probe that I said at the beginning. Never forget about that, or you will regret this. And you put this on enable, and now we are at like 50 frames per second. It's pretty good. So just in like 6 minutes of debugging, you can already do a lot. Maybe one last thing before I hand the project to somebody else is also that we don't have the selection, and in SRPs you want to use custom render passes for this more than actually multipass, which can be less convenient. So same thing in the package manager. I had some full screen samples that I can directly use actually. Like there is a custom pass full screen sample which has a highlight sample for you that you can check. And here, like if I go there, I just have to enable it on like the characters, and I have my highlights. Of course, there are some tags which are tag character, but it's there. So pretty cool. We took almost like 16 minutes to go from a built-in scene to like a kind of almost like the triple version. No, I'm exaggerating, but like and optimizing it. I hand it over to Onat for the last part.
Just switch this again, right?
Yes. Oh no, sorry.
No, slide first.
Oh, yeah.
Oh, you remember that?
Oh, yeah.
Okay.
Did you want to,
No,
did you
no,
want to
it's okay.
say something?
No, no.
Okay, yeah. So, hi, everyone. My name is Onat, and I'm the director and composer of Halibut. For those of you who don't know the game yet, Halibut is a handmade narrative game about friendship and life on a spaceship stuck undersea. What do I mean with handmade? Well, for our asset pipeline, we build sets in the real world and puppets like this one for a stop-motion film, and then 3D scan everything to bring it into the game. The actual 3D scanning process has been simplified here in this video, by the way. It's unfortunately not as easy as that. Well, here is a short trailer about the game from... this.
Maybe we can dim the lights for the trailer so that
Yeah.
it's better.
Thanks.
Oh.
Yeah.
Can we dim the light?
So, why HDRP? Since the beginning, we wanted to create a very cinematic experience. Among our goals were to recreate the handmade models that we built in as close to as possible in the digital world as well. To create a look that feels grounded in reality, that really feels close to what we built in reality, and also to optimize performance. In fact, we started building the game with Unity 5. It's the first idea for the game we had 13 years ago, and we actually started working in Unity around 10 years ago. At least physically based rendering was available already. So we did what everyone recommends to not do, though. We always kept updating the engine until 22.3, which helped us to bring the visuals from this, which is our first prototype in Unity 5. I think this was around 2015, to this, which is the current state of the game, basically. And we switched to HDRP when the first public version of HDRP was available in around 2018. We did some quick tests and immediately noticed that some things that were really important for us. So already in Unity 2018, in the first version of HDRP we noticed the realistic light fall off, the great-looking specular reflections, which just made our models feel more real, the great colors, tone mapping, physical lights units, and physical camera, which for me personally is very important because I have a film background and I could work the way I'm used to working. And then also the integrated post-processing, which, because everything runs or uses the same passes for some stuff, actually optimizes everything a lot. But a lot has happened since then, and so many great features were added that became essential to our game. And I want to jump into the editor and show you some of the amazing features that were added since then. Okay, so you see one of the many timelines of our game here. So pretty much every single, let me set this like this. Okay, pretty much every single dialogue and in-game cinematic in our game is created using timeline and cinemachine cameras. You can already see the beautiful physical depth of field. I already mentioned I have a film background, so for me it was really important to work with the values that I know and achieve the effect that I know how to achieve in the real world. So because of the post-processing that is connected to the physical camera, you can now adjust the focal length of the camera to influence the depth of field of the camera, for example. Which means with a wider focal length, you have a shallower depth of field, and with a longer lens, you get a shallower depth of field. So, and that's not only by using the focal length, but what's even more important, it gives me the ability to control the amount of depth of field by adjusting the aperture of the lens. And it's not only the amount, but by using, for example, this anamorphism slider, I can even affect the bokeh of the lens to basically give it the lens feeling that I want to have. But yeah, let's bring this back to 1.4. All those physical values are also true for the lights, by the way, which I really love in HDRP, that I'm able to use physical light units. But I'm going to move to the more interesting things. You can see one of our beautiful alien characters here. And one thing that I really loved to actually make these puppets or create these digital representations of our physical puppets, it was really important to get the materials right. We are using a subsurface scattering material here, and it gives us this really soft, waxy look almost. You can also see it on Harold's face, if I look at it, especially when I'm switching back and forth between this material and a more normal lit material. So let's bring this to Charlotte. This is the one we are using for the plastic parts or so. And you can already see the way the normal map is displayed, it gets harsher and so on, and more artificial, I would say, compared with this thing. By the way, this effect is even more noticeable once you have shadows in the facial areas, for example, because these are also softened through the subsurface scattering. It's really nice. And also, HDRP enabled us to, I'm not a programmer, or I haven't been a programmer, I have now learned how to program, but shader programming is still something that I've never done. And shader graph and all the different master nodes enabled me to create something like this alien cape material, I would say, which we did by using one of the master nodes, the iridescent master node, which already basically creates this iridescent effect, and the only thing we did in this case was add a bunch of animated noise to it to, have these colors animating, but the color production, I would say, is basically done by the actual, physically based iridescence, right? Yeah. One thing that was really important for our game, I already mentioned that we are scanning all the assets in our game to bring them into the game. And You can imagine we don't have any tiling textures in the game, so every single centimeter that you see here is basically unique. Now, we also ship the game on consoles, and you can imagine this wouldn't be possible with a traditional texturing workflow. So while it's still experimental tech, virtual texturing was basically essential technology for us. And you can see how detailed every single one of those textures are. And I'm actually, let me quickly switch to a debug view of that to show you. So what virtual texturing basically does is, I'm so bad at multitasking, by the way. Okay, so it breaks down the textures into, it subdivides them in much smaller tiles, basically, and only streams in the tiles that are actually necessary. You know, I love this debug view because it kind of shows you how the process works. And there is also an option to disable the screen space requesting. So now everything is basically stays like it is here, and you can see all the stuff in the rest of the cave isn't even loaded in, or not even the details on the backside of the character's head. So that saves a lot of memory, and the cool thing about that is that I can actually define the amount of memory to be used, and I can set this based on the platform, for example. And on the consoles, I have a not so high limit, for example, for what the textures should use in terms of memory. That really helps get things under control. Now I'm going to move to another scene to show you two of my favorite features in HDRP, actually. Starting with APV, which, by the way, it's also available on URP right now, right? Yeah. So APV is basic, or adaptive probe volumes, is the replacement for the light probes. But for us, it was much more than that, because we actually didn't just use it to, apply our baked lighting to our real-time objects, but as you can see here, we don't even have light maps baked, even though most of our game's lighting is baked. So we are basically also using the data, the lighting information stored in the adaptive probe volumes for our environments, for most of them. We still use some light maps here and there. And the cool thing about that is, first of all, the baking times, which are super fast, and also the consistency. So if I bring Harold, for example, over here, you might have noticed it sometimes when you try it out in your game or so, that there might be inconsistencies between your baked lighting and the indirect lighting applied through your light probes to your real-time objects. And you can see everything looks very consistent here. And additionally, what you see in the background is this is the way we created the underwater world, which is basically just a volumetric fog and lighting. Before we used APVs, all these lights here were real-time lights with volumetrics. It was still kind of efficient because HDRP scales really well. But again, because APV is able to use apply baked lights to volumetrics as well, we switched all these background lights to baked lights now, and so they don't cost anything anymore. As you can see, it's all baked. And again, to bring my Herald over there, it doesn't only affect the volumetric fog, but of course it would also affect a submarine traveling around there, for example, which I'm mimicking now with my Herald character. And you can see that the lighting is realistically applied here.
Maybe show the debug view of the rendering of the probes.
Oh, yeah, true. That's a good idea. So there is obviously
Display probe.
Yeah. You can see all the probes that are automatically placed for me here. By the way, also in terms of authoring, it helped a lot, because instead of, every one of you might know how tedious it is to place light probes. This process is basically automatic. So you set what you want to be the maximum density, and you can see that around things, it's denser than, further away it gets, more and more sparse.
How long does it take to bake?
It really depends. Hard to say. I think this scene, because we said it really dense, it was around like 10 minutes, 12 minutes, something like that.
Okay.
And it also depends on the machine, obviously. So, but yeah, it's definitely faster than baking light maps. And the most important thing in our case, because all these are, things that make both the workflow better and the quality better, but aren't game-changing in terms of, in our case, there was one feature specifically which otherwise we wouldn't have known how to do, which is blending lighting scenarios. So if I switch to the Pro Volume settings here, you can see we have 2 lighting scenarios, which means we have 2 different lighting setups baked in here. If I can actually click on them to see the different lighting. It's only halfway applied right now because the real-time lights that you see there don't change. But we basically have a little script that changes the lighting in the scene and bakes the second set. And then in gameplay, if I move into the gameplay, there is another little script, which is our lighting manager, which in the same time sends a signal to basically switch the lights or blend the lights, change the look of the real-time lights and the emissive, the emissive object, and also blend between one lighting scenario to another. And if I invoke night, you can see I have a really nice transition to a night setting, and then also back to a day setting. Wow. And this all works with baked lighting, so we don't have any real-time global illumination in our game, which we aren't even using SSGI, which obviously helps a lot with the performance, and that's performance that we can spend anywhere else. I shouldn't have left play mode actually, because there is, I can move over to the next really cool thing, which is STP, because we were talking about performance already. Again, our aim was to deliver a high quality game on PC and consoles while not compromising on performance. And right now on my laptop, which is a beefy laptop by the way, but I'm still only able to run the game fluidly in 1440p. Mathieu has already showed you a little bit about STP, but just to give you a quick glimpse again, there is also, can go to the live stats here. No, too many little windows. Okay, so let me switch this to 4K, and okay, like this. So you can see that we are CPU bound in this case. Oh. And we are running at like 17 frames. And that's because STP is disabled right now. I'm going to enable it here in the GPU bound. What did I say? CPU bound? Yeah. GPU bound, obviously. So I'm going to enable STP, and it's set to maximum performance right now. So that means we are rendering like only a third of the resolution. I actually have to zoom in so that you can see the quality difference, maybe. Yeah. Okay. So you can see while we are rendering only a third of the native resolution, so in this case it would be, what is it then, 1440p probably, somewhere around that, natively, and upscaling to 4K, it looks really well. And we have improved the performance, as you can see, to 40 frames already, and we are not GPU bound anymore. Now, the crazy thing was, I still don't understand how STP works, honestly, because even if I switch to full HD now, you can see that it doesn't look perfect, but it looks quite clean, and the difference between STP and other upscaling algorithms gets clear whenever I switch from STP to TAAU, for example, with the same scaling, so only rendering a third. And you can already see this is like quite a bit blurrier and more pixelated and so on, looks kind of broken. Which, is kind of clear, because right now we are rendering at an internal resolution of like 300p or so. And, but yeah, somehow STP still managed to make something usable out of that minimal resolution here.
And it runs on Steam Deck, right? Like,
Oh yeah, it also runs on Steam Deck. Like the game runs on Steam Deck really well. Yeah, and that's also thanks to STP and on consoles as well. Yeah,
So
I think that's it.
yeah. Okay, so sorry. I hope you enjoyed, and if you have questions, come and see us after. I hope you have like a better overview of like all the things you can do, moving away from built-in render pipeline. And yeah, thanks a lot.
Thank you.
Thank you.